You guys hear me?
Yeah, I can hear you.
Okay. Why is everybody's camera off? Except for Byron.
Well, even then, I didn't necessarily want to turn mine on, but I'm in the library because I have 3 back-to-back classes, so can't do it at home.
Okay. Let's see, we got 9 people. How big is this class? I don't know. Let me look.
I don't think it's a very big class.
I don't think so either. My OOP class was tiny. Oh, there's 20. That's still not huge. Okay. Let's see. 10 people are here. I'm gonna wait a minute. Just stare at you. Hey, when I logged on, y'all see my picture? There's a painting behind my head. It's like white and it looks like I have a big afro of white hair. I really was like, who is that old guy? That guy's got crazy hair. And I was like, shit, that's me.
You should grow your hair like that.
I'm serious. You get old, you don't, your self-image is not what, you still picture yourself as a young guy. It's crazy. Oh, 15, we're getting there. Let me just share my screen. Okay. I'm gonna be more organized this semester. I say that all the time, but I really am. Where's our repository? So I went over our topics list and I actually made it a checklist. So we're gonna check these off as we cover them. One problem is that when you start talking about data structures, and I gave an example here, like there's array-based implementations, list-based implementations, and variations on each, singly linked lists, doubly linked lists, circular linked lists, yada, yada, yada. But like just to implement a priority queue, you can use an array-based implementation, storing a binary tree in an array. You can implement a priority queue as a singly linked list where you order the items. And you can even use a circular doubly linked list, and it's called a Fibonacci heap, but it's still a priority queue. So my point is, somebody needs to mute their mic. Who is that? Okay. There's no real way to stay on a single path that just says goes boom, boom, boom all the way down. So there's going to be some jumping around. Okay. And so we're just going to have to deal with that. You guys, it's kind of expected you guys to know array-based versus list-based, but just like my OOP class, the only thing I can assume that anybody has had in this class is 1063. So I'm going to start almost like I did OOP this morning and go over writing some code to implement a linked list. And I'll probably do a singly linked list and a doubly linked list today. So let's do it. You guys ready? Okay. So let's see. Singly linked Spring. I better put 3013 because I bet I have a singly linked list somewhere. Well, I don't know if I aimed it the same in OOP this morning.
But the spring 2021.
Yeah, you wrote 2020 or something.
I did.
Yep.
Well, how about we just jump to the future?
Fine, let's get this year over with.
All right. So I mean, because these concepts, they're so important. So That's why I start off in both of in OOP and in algorithms with them. So, you, I feel sorry for like Conan, Mr.
Ah,
Light.
that's good. Shit, I get both ways.
Okay. All right. So let's do a singly linked list, then we'll do a doubly linked list. And I'm gonna maybe instead of storing just numbers, we'll store something a little more hefty, like
Names.
let's do names and ages. So let's say struct. We'll just call it a person. Okay. Now, difference between a struct and a class.
Name.
Struct defaults to
Public,
public, class
class defaults.
defaults to private.
Okay. You all, I think everybody was right. This is all public and this is all private initially, unless you tell it otherwise. So in our struct person, we're going to have a string data type called a name, and we'll have integer age. I would put weight in there, but I'm so fat right now, I don't want to even think about it. COVID has killed me, and I drink too much. Stay at home. I'll turn my camera on, you'll see a bottle of bourbon over there. It's sad. So in our struct person, what is a struct really? I like to use them just as a collection of data. So this is really just a little container that stores a name, and it stores an age, and it just keeps them together. So we're going to use this person as the data type for our list. So we also need to create a node. Dang it. I meant to go to that Google to draw stuff. Let me go look at Slack real fast.
MS Paint?
No, Jamboard. So I don't have any recent jams, whatever does that mean? This is a drawing app, right?
So I,
That's what that one guy said.
yeah.
Actually, you had to have a Jamboard to use that.
Oh, well, I have an untitled jam.
Maybe not.
Stupid. All right. That was a sad attempt. I'll be ready tomorrow with drawing stuff. In my struct node, what am I going to hold? I'm going to hold a person. We'll call them data because it will be data. And in a linked list, and here I go with my drawings again on my piece of paper. Let's just assume okay. So I got to see me. Where am I? There I am. All right. So with our linked list, this is the head of our list. So head is a data type. I mean, it's a variable of type pointer that points to, it's going to point to a node. Each of these nodes that I drew is going to have, the data section is going to have a type person. And then each of these also has, you can think of it as two sections. You got the place where the data is going to go, and then you have a pointer that points to the next node. So yeah, so here person is being used as a data type called data, and in our node, person's going to go there. And then the next thing that we're going to do is add a node pointer next, and
Yeah.
is going to point to the next. What?
If you go back to the Jamboard, in the bottom right-hand corner, there's a yellow plus sign or yellow circle with a white plus sign. And I'll let you create a new jam.
But I thought I did click that plus sign down here. Okay, there's my new jam. Oh, there's drawing stuff over here.
There's drawing stuff.
So this is is this a pen?
I think the top one's the pen.
Okay. Oh, this is gonna be bad. You can't do letters.
Yeah,
So we're gonna say no, that's all right. H. points to, yeah. Yeah, I'm doing, I need to practice on that. That's horrible. Sorry. Thank you, though. So we've got a person, which is a data type. So every time we use a struct or a class, another way to think of it is in OOP, I mentioned it's called an abstract data type. We're creating our own data type so that when I say struct person, I can now use that as a data type to implement a variable. So I'm just using person as a data type in my node. So we're going to hold a person as data, and then we're going to use node pointer next, which is the generic way to point to the next thing in the list. Okay. So this is the basic structures that we're going to store. And this is a structure that's going to help us link things together. So a list still has operations, right? We can define what we want those operations to be, but mostly it's like push, delete. Let's call them add and delete, so we're not getting confused with a stack or a queue. So operations, we can add a person, we can delete a person, we could find a person.
Get the size.
We can get the size of our list. We could even probably update a person. We're not going to do all this today. Where you find a person and you would edit their information, like change their age or something. But mostly I think we need to do add and delete, because deleting from the middle of a list as opposed to deleting from the end of a list is different. So let's start pretty generic. Oh, crap. Hold on. There's a problem with teaching from home. UPS. Interrupting class, damn it. Okay. So another decision we need to make is insert items where? Like, do we want to keep them in order? How do we want to keep them in order? Do we want to, because we could create, really quickly, we can turn this list into a priority queue. What's a priority queue? Priority queue, just thought somebody might know. A priority queue is just a container of items where the thing with the highest priority is in the front or on the top. That's it. So if we wanted to say old people have priority, they stay at the front of the list. Or if we just want to order based on names alphabetically, we could do that. Let's do order alphabetically just to keep things interesting. So we're going to do an ordered insert. This might take us the whole class, but that's all right. All right, so we're going to do an ordered insert. We're going to change the name of our list to ordered list. And yeah, let's get moving. So what in my class, if I want to create a list, I need to add a constructor. Constructor is a function with the same name, blah, blah, blah. I sound like a robot because I say it all the time. So what do we need to maintain a list? In my picture, what variables do you see? You see a few nodes. The nodes are self-contained. There's only one external thing, head. So we probably need something in our list to represent the head. And it's a node pointer, and we'll call it head. So to initialize a list, all you do is say head is equal to null. And so what that does is it takes head and it makes it point to nothing. And you know when head points to nothing, null, that it's an empty list. Okay, Byron mentioned size. So let's say integer size, we'll keep track of that. And we'll set size equal to 0 right off the bat. So this really is constructing things. It's setting everything up for us to get ready to use a list, to create a list. So constructor initializes everything. Is that it?
I might add a tail pointer as well once we start adding stuff to it.
Okay. So what Byron just mentioned was a tail pointer. And the tail pointer just points to the end of the list. Now, depending on how we implement things, this could be helpful. And then when it can be helpful, I'll bring it up again. But it's just something that maybe we could bypass. Okay, when you insert items into a list, you've got a few choices. You can just stick them in the front, right? And everything that goes between head and the first node, that simplifies your code. You could stick them at the end of your list, but if you didn't have a tail pointer, we would have to traverse the list to get to the end every time. That's expensive, and that's where a tail pointer could be helpful, because if you just always wanted to stick it at the end of the list, then you just stick it in between tail and the last node. And since we have direct access there, it makes it a lot more efficient. However, we're going to do an ordered insert. So we're going to start at head and we're going to march down. So like if I had ant, bat, dog. So let's say I wanted to insert cat. We have ant, bat, and dog. Cat would go between the bat and dog, right? So we have to figure out by marching down and locating that position of where to put the node that holds cat. So we're going to have to traverse the list almost every time. But we could compare if I wanted to insert the word eel. My vocabulary is pretty kid-like. Cat would go there. We'd still have to traverse, right? But eel, what do we notice about eel? It's greater than dog, right? When you compare strings, you just E is greater than a D. So eel would go at the end, right? So we could make a few comparisons right off the bat. First thing we do is the thing we're inserting less than the first node. Then we do what we call a front cert. Is the thing we're inserting greater than the last node? Then we do what we call an end cert. Is the thing we're inserting not greater or less than head or tail? Then we do what we call an ordered cert. And then and only then do we have to traverse the list. So we're going to be smart about this. So I'm glad Byron brought up the tail pointer, because we'll use that as an insert method now. So we're going to have 3 insert methods. Let's change it from add to insert. So we're going to have void front cert, void end, we'll call it tail cert. No, I don't know. Why am I even worried about it? End cert, and then we have void ordered cert. Okay. Let's also throw down here for now, void print. Okay. Beth, come here, lay down. Stop clicking around. So when do we do a front cert?
If the value is less than the head.
Okay. Value less than head of list. Okay. Insert is value is greater than head of list. And then ordered cert is value somewhere in the middle. Okay, now these are all public methods, right? Shit, what? That's confusing. So if down here I said, what do we call list? Ordered list. We said ordered list L1. Okay, now I want to insert some stuff. I don't even know what I'm inserting yet, but L1 dot, I don't know, what am I calling? Front, end, middle. So the point is, these aren't really good public methods. We're going to use them, but they're really kind of private, because publicly, whoever's inserting, they don't give a shit about front end ordered. All they know is they're expecting an ordered list based on name. Okay. So all they care about is there's an insert method. And our insert method, they are going to decide which one we're going to use. Okay, so if we're going to insert something, we're obviously sending in a person. Not obviously, but we're passing in a person. And I need to create a node. And I need to know, do I create the node now? Or if I create the node here, then I got to pass it to one of these. Or do I just wait and create it in each of these separately? See, these are all choices we got to make. And none of them are wrong. I could argue that if I allocate memory here by saying node pointer temp is equal to a new node, and that node expects a person, or it should. Oh, we didn't put a constructor on our node. So let's construct our node. Node person P, and we're going to say data is equal to P. And then we're going to say next is equal to null. There might be some issues here, but we should be good. Okay. So then down here, no more red, we allocate memory. Okay. And I need to test now. We already know head is null, our list is empty. So our current picture on my super amazing, technologically savvy piece of paper, our picture looks like this. I never thought I would be the old guy, but I turned into that guy. All right, head is null. So up here is just notes. This is our list, it's empty. So when I say insert and on code here, wait, you guys can see it when I lift the paper, right? Even though I'm sharing the screen?
Well, I have to pin your actual image and then go with the other one.
Say that again?
Your little screen, I have to toggle between them.
Yeah, okay. That's what I'm staring at myself over in that like list of people, like the grid. Okay.
Yeah.
Just split the screen.
You can split the screen?
Yeah, side by side with the speaker, so you could see. I could see the two.
That'd be-
Yeah.
Okay. Just as long as y'all can see, because I don't know, sometimes I forget what's going on. So we insert a person, we allocate new memory. Now we decide, where does this person go? So we have to do a comparison. We have to say, is person less than head? Is person greater than tail? Or middle, whatever. But we also know that if the list is empty, so if not head, this is still just really easy, right? There's no list. In my empty list, I know there is no test to go front, back, middle. It just, we need to add a node. So we're going to say head is equal to temp. And so now we have a list. Let's say we're adding Chuck. Chuck is 81. And Chuck is amazing. So my new list has Chuck in it. Okay. All right. Next, we add another node. So my other node, depending on what the name is, let's say it's Samantha. Sam for short. Sam is 8 years old. She doesn't know what she's doing here, and she's been crying the whole time. So we need to know where Sam needs to go. Sam is greater than Chuck. Okay. So what we could do is say, else if, what am I looking at to make the comparison? Temp is a person, right? Temp dot, so we have a node, which is a struct that holds a pointer and a person. So how do I access the data element in my node? I use the dot operator, correct? So here I'm looking at temp.data, okay? But wait, it's a pointer, so it doesn't like it. That means we use the arrow operator. What is it we call that? So this says no viable conversion from standard string to bool. Yeah, it's complaining. We just want to access the name right now. So is greater than. So compilers are there to mess with your mind. You see the big red line, and even I start freaking out. I'm like, what am I doing wrong? I'm not doing anything wrong. It's like, damn it. So I want to compare temp's data.name to head's data.name. Now this might be a mouthful for the first day, but we might as well get used to it because we're going to create some crazy stuff. So temp, we use, since it's a pointer, we use the arrow operator to reach into the node to find the data section. And then the data is not a pointer, so we use the dot operator to look at the name. So this is going to compare their first name, Chuck, in this exact instance, the other name, or this is Chuck, this is Sam, and we want to see if it's greater than or less than. So if the name that you're passing in is greater than the name at the head, do we know what we're doing? That implies an ordered middle insert, right? So that's not helpful. So let's test for less than. If the name that we're bringing in is less than the name at the front, then we know we do a front cert. That's clear. So we'll say front cert, and we'll pass temp up to front cert. Now it's complaining because our method is not defined like that. So we need a node pointer temp. So now it shouldn't complain because we're going to pass that node in and it'll link it in. Okay, we'll go implement that in a second. Else, if we're going to check the end of the list. So if temp data name, what we just passed in, is greater than tail data. Ooh, I made a mistake here. Tail is equal to temp. Right off the bat, if you have one node, head and tail should point to that same node. So, because it's a list of one item. So so from lines 63 and 64, we make sure that head points to the single node we've inserted, tail points to the single node we've inserted, and we're good, we're set. Then we go to the else. If there is a head, meaning we have a node, we check, hey, are you less than head? If you are, we do a front cert. Are you greater than tail? If you are, we do an insert. And it's complaining because insert also does not expect a node pointer temp. I'm just going to call this X. And then ordered cert will be the same, node pointer X. Okay, so then if else, if it's not either the if or the else if, then the only thing left is ordered cert. Right? Come on. This reads pretty good. Is everybody kind of with me?
Don't you overload the greater than equal than operators to speed up some of that?
No.
Like where you just do, or couldn't you just like compare nodes instead of having to write out all the logic like that?
Yes, but we're not in OP. But
Okay.
you're Byron, you're absolutely right. And everybody's gonna get pissed, but you guys are gonna have a homework now. I'm kidding.
Don't
Byron's
do
right.
that. Don't
So
do that.
OOP, we would overload these operators so that we would say if temp is greater than tail, and then it would know what to do. In fact, I might add that after the fact, but we don't have time right now. And this is algorithms is just about down and dirty. Let's make stuff happen. OOP is about design and cool, pretty shit, and we're not there. So we're just going to compare, dig in there and compare them. All right, so but it reads pretty good. I think we've got insert a person, allocate new memory. Then we decide, where do you go? Are you going to the front, you going to the end, or are you going to the middle? And the only thing that this ordered insert would suffice to get everything in order, no matter what. The only thing these first two are doing is, hey, if we can do an order of one operation, meaning we're going to talk about complexity next week, but a big O of 1 is the best complexity you can get. Big O with any constant is considered nice, fast, right? Right now, if we just did an ordered insert, we would do, it's an order n operation, because at worst case, you got to look at every node in the list, where n is the size of your data set. So we're trying to at least capitalize on an order 1 operation, another order 1 operation, and that third one would be an order n operation. And we only do this, however many times you have to insert something in the middle. And it all depends on the order of your data that it comes in as well. If you already have ordered data coming in, you could really capitalize. It would be really fast. You would maintain that order, but you would still have these constant time insertions. So we're being pretty smart. Okay. So we don't know if any of this stuff works. Let's actually implement some of it. So in a front cert means that the node goes in between head and the existing node. So we only need to update 2 pointers. We need to say X next is equal to head. And all of these methods, obviously they have access to head because they're in the same class. And just because you're public or private, they all have access to the same stuff. So we point next equal to head. What does that mean? Let me draw it out a little better. So I'm just going to use big letters. Okay. So head right now points to a node, it's got an E in it. Now we're going to implement or insert a node that has a C in it. So the constructor of our node up here says, hey, next is null. So we know that's true. It puts the person inside here. And so our front cert says X node X next is equal to head. So this is X and its next says what it points to. So when you set two pointers equal to each other, they point to the same thing. So head's got the address of this node. And so it says X next equals head. So we want to take the address of what head's pointing to and stick it into next of this node, which essentially makes it point to what head's pointing to. Now we can update head to say head is equal to X. And so head will now point down. So head points to this. So we have to update this node first, because if we said head is equal to X first, we lose the entire rest of the list. So that's why we did it in that order. All right, let's look at insert. So now I'm going to insert a node that starts with a W. Okay, so it has, it points to null. It's got a W. We've already tested in our insert method, and it's greater than tail. So we come up here, and we need to update pointers. So what am I doing? It's the same idea. So we're going to say
Setting next to the tail and then tail is equal to X.
no. Wait. Oh, if we said next is equal to tail, and then tail is equal to X, it looks crazy.
Make that tail equal to null.
Yeah, we don't need to update next. We really just need to link it in by updating this tails next points to the new node, and then we update tail by pointing tail to the left. God, this got ugly. No, it's hard. Even on a whiteboard, when you got plenty of room, it gets crazy. So we've got two separate entities right now. We've got a list, tail points to the last node. So the order of operation here is we link the new node in. So tail next points to the new node. Let's do that. So we're going to say tail next is equal to X. Okay, so we're going to do that. We're linking that node in. It's the same, but the opposite order of what we did with head. So now that node is linked in. However, we now it's the last node in the list. So we've got to take tail and move it down. So then we say tail is equal to X. So that takes the actual pointer tail and points it to X itself. And our list is ugly, but you know what? That's what it looks like in memory. They're not contiguous, pretty like an array where everything's in order. You get what you get. And that's what makes lists a little hard. There's more overhead. but they can be pretty powerful is if you can keep track of all the pointers. So let's test front and end and then print out our list because we want to, because one thing when you're writing code, you want to lock down some methods and they work, and then we can just put our blinders on, and when we start getting weird errors, we know that we vetted them, right? And so we can ignore them. So I'm writing a lot more code in a row than I want you guys to write some code and compile, write some code and compile. And then as you get more and more comfortable, you don't have to compile as often. So we use our print method as our debug. So I'm going to say node pointer current. I'm trying to use the same variables I used this morning, is equal to head. And then so we're going to say while there's a current, remember, if head is null, this loop will never even loop, so we're good. If head is not null, it points to an address, then current will have value in it. It won't be 0. So this evaluates to true, the loop executes. And then to traverse a list, you just march down, going current is equal to current, next. And once next is null, the loop will stop. All the cool stuff happens here. This is a generic traversal. I said it this morning. I said it OOP. I'll say it probably every time I teach programming. You memorize this, you're good. So then we add where does the cool stuff happen? We're going to say cout, current, arrow, data dot, name. What is it not like?
Capital N.
Huh? Is it?
Your name was capital, wasn't it?
Okay. See, and I did it this morning. Look, capital N, lowercase a. That's pathetic. Let's get consistent. We're going to capitalize all this. So capitalization is going to matter. And we're going to replace it with next. Replace all of them. Data. Data. Replace all of them. Anything else? Just look for the red lines. Oh. Okay, see, stupid red line. It made me think. So we haven't even touched age yet, right? It's whatever. I'm worried about this assignment. We might have to be more explicit. And if it crashes and burns, we'll know why. So we're going to create a list L1, and then what does L1 want? It wants a person, right? Part of me thinks we should make a person pointer instead of an actual person, but that's okay. So we're going to say person P1 is equal to P1. And then there's a constructor. So we're going to say Abby, comma, is 67 years old. And it doesn't like it. So there's no matching constructor. So what is a person looking for? A person doesn't have a constructor. So person and string or int a. Name is equal to n. A is equal to age is equal to a. And then we're good. So what is this not like? So what it's telling me is constructor for node must explicitly initialize the member data which does not have a default constructor. So we're gonna put person with nothing. And so we're gonna say name is equal to an empty name, and then age is equal to 0. This is a default constructor, no parameters. We just initialize all the values. So now it's a little more happy about person P. So it wanted a default constructor because one of the compiler's jobs is to create a copy constructor to actually do the copy. And it should be fine when we say data is equal to P, because it should create a copy constructor that is expecting another person of the same type, you know, so that it can copy each element over. So I think we should be good. So we got Abby. See, this is the problem with not pointers, is we need separate variables for each of these people. And I'll show, we can change it to pointers a little later, but I don't know where I'm getting these names. So we got an ordered list, L1. Now we want to only use front and insert, right? So first time shouldn't matter. So we should say L1 dot insert. And we're going to insert P1. And then we're going to say L1 dot print, because we need to test right off the bat. Boom. I'm liking it. Let's do the same thing we did this morning. Cout, or if current next. Oh yeah, we capitalized everything. If current next, cout a fancy big time graphical arrow. And then outside of the loop, we're gonna cout an end line. Actually, cout no. Where's that end line? Why did it do that? What?
There's no cout right there, so you're just printing the arrow and the null.
Yeah, no, I know, but if we don't do, everybody gets an arrow, and at the very end we just point to null. But why did it do an end line in between? Where's after Abby? Oh, I'm an idiot. Sorry, guys. Okay, so Abby points to null. Now let's, if we insert Chuck, where's Chuck gonna go? Well, it's an insert, right? Chuck,
For Abby.
yeah. So let's insert P2. We run. Okay. Now, if we did P3, we still get an insert, right? So I'm gonna insert Chuck first. And then if I insert Abby, we get a front cert. And then if I insert Donnie, we get an insert. And we kind of hopefully verify that all of the methods work. We good? Badass. Awesome. Come on, this is fun. This really, I could do this all day. As trivial as it is, as many times as I've written a list, it's like you're taking control of the computer. You're like, yes. Maybe I'm a control freak. Ask my wife after she beats me, but it's cool. All right, so the ordered insert, how much time we got? We good? We got plenty of time.
Got about 30 minutes.
Okay, we're good. So the ordered cert is where all the meat and potatoes are, right? This is where we have to traverse the list and figure out where we're going. And let me clean up, create another, oh, my expensive notebook. So we've got a head that points to, we got whatever, A, that points to an F, that points to an M, that points to no. And we've got a tail that points to. All right, so here's our current list that we're going to be picturing in our brains. We got an A, an F, and an M. So we got plenty of gaps that we could insert into. So when you insert into the middle of a list, there's a little bit of an issue. So we know we need to traverse. So let's write a traversal. So we're going to say node pointer current is equal to head, and then while current current is equal to current next. Okay. Now I'm going to add a few more people in here. So this is so stupid. We need to use a pointer. I'm embarrassed, but because we could reuse the same pointer over and over. Anyway, so Donnie, what's an E name? Echo, that can be a name. Marky Mark, don't even know where that came from in my head.
What about the Funky Punch?
Well, Funky Bunch, if we did it now. No, we need, what's after M? There's a bunch of letters and a bunch of brains.
Raphael.
I was watching a comedy special with Kevin Hart, one of his latest ones, talking about all the women he used to talk to, and he called like Ethel, Agnes. He's like, yeah, they were a little older. They came up with all these old names. So ordered insert. So let's make sure this runs. And I gotta hide you guys. Oh, we never inserted them. We'll finish today. Okay. Okay, so looking good, right? Right, so now we want to insert into the middle somewhere. So to do an ordered insert, we traverse the list. So while current, we could say while current and current, is it data? Now, we also need, we pass in node X, right? So what we're doing is we're marching down. So let's say in this instance in my picture, I'm going to insert echo. Now, yeah, echo will, no, not Raphael. I'm actually doing the alphabet in my head. Golf. We're going to insert something with a G. Holy crap. So we've got a G node. And hold on. And then, so this G, we're going to march down current, and we need to know when to stop. So we know current can't come to the end, because if it gets to the end, well, we're doing an insert, it don't matter. So we got to compare. Is the data section in this node greater than this one? If it is, we move down. Is the data node greater than this one? If it is, we move down. If it's not, we need to stop traversing the list. So that's what this is doing. Are we on the list? And if we are, is the name that's in the node that we're traversing by less than X's data.name. So this is comparing the actual data value, and this is making sure we stay on the list. And then this is moving us down the list. Okay, so this will basically move us down the list until the name we're looking at is no longer less than the name we want to insert. All we got to do is change this sign and we reverse the order of our list. Okay, but there's a problem. So let's look at this. So as we insert, we compare G to A. So is current data.name A less than X's data.name? Yes, this one is less. So we move down. And then are we still on the list? Yes, we are. Is current data.name F less than X's data.name? Yes, F is less than G. So we move down. And then we say, hey, are we on the list? And is current data.name M less than X's data.name? No. So we would stop here because, well, the loop would end. So current points at that M node. There's a problem. This bad boy needs to go in here, which means this one needs to point to me, the G. G next needs to point to current. There's no way in a single linked list to link this bad boy in unless we add another pointer. And that's what we're going to do. So we're going to add node pointer previous is equal to head. And then so every time we increment next, we'll say previous is equal to current. And then we'll update current. So when it's all said and done, since we say previous is equal to current, and then we move current down, when we're done with this traversal, previous will be pointing at the node before and current at the node after. And so we've got control over all the pointers we need to link this new one in. You guys fading? You still with me? Okay. So now the action is down here. So try to keep my picture up, but what pointers do I need to update? And what order should I update them in? So I'll tell you this, we need to update previous next, and we need to update X's next. But the order doesn't matter. It does not matter. Because previous and current, they're keeping a hold of both sides of the list for us. They're like, they got it grabbed on. So usually if you have like one pointer and you do things in the wrong order, you could lose part of the list. But in this instance, I don't think it matters. So if I were to say previous next is equal to X, okay. So that says previous next points to X, and then X's next points to current. X is a bad variable name. I don't know why I switched to it. It doesn't fit the theme. It's all lowercase and little and non-explanatory, but oh well. All right, so this should do it. And so we need to test it. Give me a name that'll fit in between one of these guys. Barbie. You guys are too slow.
Gerald.
Gerald? I'll go with Gerald. Gerald is 23 years old. Gerald is a Scorpio and he likes long walks on the beach.
Just come out your head.
This idiot. I'm an idiot. It keeps y'all listening. That's my job. You might be laughing at me, but you're listening to me. All right.
The dating game.
So Gerald will go between Echo and Marky Mark. Holy crap. Bam.
Yep.
See, it's fun. This is awesome. Give me another one.
Daphne.
That's a good one. Daphne is 24. She is also a Scorpio and she likes MMA. Didn't see that one coming, did you? All right.
They're more along the lines of solving mysteries.
So Daphne is greater than Chuck, but less than Donnie. We're awesome people. All right, we have an ordered list. This ordered list has a head pointer and a tail pointer. It's got one generic public facing method called insert that controls three private methods that only it knows about, data abstraction, and it calls the correct method based on the value of the person's name. If in our ordered insert, if we change this value here, I think we reverse the order of our list. Oh boy.
Stop it.
Yeah, because our front cert, we'd have to change those signs too. So let me go to front cert. No, the signs are here. So we got to say, flip. Did I flip it around? I think so. Okay. Yeah, so we just flip those three signs and we reverse the order of our list. So
Just do that in the print function. Just print it in reverse instead of flipping the logic there.
no, because
Like, aren't you printing from the head? Couldn't you print from the tail and then just reverse it that way?
yeah, but if there's other operations that are being performed, the order of the list would matter. But you're right. If we just wanted to display them in reverse, we could change the print method. But if you're doing operations based on a specific order, not just with people's names or whatever, we would want to be very consistent. And this is the algorithms part of this course. Is with almost every data structure, you have a very specific algorithm that controls how things work, and it controls everything so that it's very unambiguous. So we would just want to make sure that whatever we did, it just was consistent, unambiguous, and was correct. But yeah. In fact, you bring up a good point. How much time we got? 20 minutes, kind of? Because I could turn this into a doubly linked list, and then instead of traversing one way to print it out, I just traverse the other way. How about I make that a homework or your first program? Turn this into a doubly linked list.
I need to stop talking then. I keep giving you homework ideas.
No, this is how I run. It's going to happen no matter what. Yeah, I don't know. I do everything based on the way you guys ask questions, what you seem interested in. That's why all my classes are different, and I always seem unprepared. I don't regurgitate much. I'm stalling because I'm thinking if I have time to turn it into a doubly linked list. Let's use pointers. We got time. Let's turn this into a pointers and read these in from a file and load them up. How's that? Okay. So let's add a file, data.txt. Okay. And then Give me my files back. Hello. Okay, so in main, we've got, let me make sure that still runs. Okay. We've got all these names, and you guys do realize person P1, P2, that's dumb, right? Either let's make an array of names. Let's do that first. No, we'll put them in a file and we'll load up an array or something. So I wonder if this will do shift option. Nope. Control, shift control. Nope. I was trying to delete a whole, like a column. What did y'all do today? We watched Professor Griffin make a text file because it took forever. So I can replace this, Command F, replace that with nothing or with just a space. Okay. And then we can say replace that. Will it do a new line? No, but just a space. Okay. And tab these over. So with a space in between, that's a delimiter and a new line. This will be pretty easy to read in. So in main, I'm going to change this up, say pound include. My dog's snoring, it's funny. I'm surprised she's still alive. Do y'all remember last semester I said she was dying? She's got little nodules all over her body, but she refuses to go away. She's awesome. So we're going to include fstream, and then in main, I'm recording this, by the way. The last recording for OOP didn't work. I don't know what happened, but I'm doing the recordings and storing them locally now, and then I'll put them on YouTube, I think. So I'm going to say ifstream fn dot open data dot text. And then I'm also going to say person p array of size, we'll just do 10 right now. And then I'm going to loop while not, let's do this in data dot, there's 8 people in here, right? And that, I'm just going to make it easy for me. So person pointer p array is equal to, wait. Integer person count. So I'm going to say or fn person count. So that reads the top value in data. It grabs the 8. So then after that, I'm going to say person pointer p array is equal to a new person of size person count. So now we have an array of exact size. Okay, then I'm going to say while not fn.eof, while it's not the end of file, we're going to say fn, well, this is an array of however many, so I need a counter now. Integer I is equal to 0. And so I'm going to read straight in from the file into person sub I, which is the 0th position first time we loop, or actually p array, sub I dot name, and then fn p array, 2 capitals. What is my deal? PA, then dot age, and it's capital. So yeah, I read in the top number, 8. Then as I create memory, and I'll comment all this before I post it, we create a counter, and then down here we need to say plus plus I, so that we move out down through the array. And so at this point, we're loaded up, the array is loaded up, so I can get rid of this. And then I can say for integer I is equal to 0, I is less than person count, I plus plus, and I can get rid of all this except for a couple of them. Well, I need to declare my ordered list. And all my declarations should be at the top. But anyway, so then this goes in the loop. All right, so what are we inserting here? We know we have a P array. We're going to insert P array sub I. And then outside the loop, we're going to print that list. Cross your fingers. Boom. Okay. Come on, this is awesome. All right, look how clean this is. Well, okay, it could be better. So now we have a data file. So this could be filled up with however many, hundreds or thousands. You read that top number as long as it's correct. And we fit the data to the list, or fit the list to the data, whatever. And we're good. Instead of having all those stupid individual variable names. What else could we do? We got 9 minutes left. I don't have time to make it a doubly linked list. What does a doubly linked list do for us?
Forward and backward.
Yeah, it just gives you more, there's more overhead, but more freedom. Like, for example, if I had a doubly linked list, let me draw this real fast. Head. So I'm not going to draw all the links. So just picture each of these little nodes that have links back, forward and backward. So that if we maintain like a pointer in the middle, and we had to do an ordered insert. So we know that if we're really having a lot of inserts, let's say in deletions, well, oh, we didn't do a delete. Now we don't have time. We'll do it next time. If we have a lot of insertions and deletions, we know we had front cert and we had insert to give us constant time insertions. That helps save some time. But if we had a doubly linked list that went forward and backward, when we did an ordered insert, we could just start in the middle and then say, hey, is the name we're inserting or the value inserting greater than or less than? And we would automatically eliminate half of the search space before we entered go find where we put that value. So those are like small improvements, but depending on how this gets used, it could be huge over time. Like limiting the number of operations you really had to do. So those are all things you have to take into account in data structures and algorithms. Like, is the overhead of using a doubly linked list, man, is that really worth my time? Is it, you know? And if it is, then you do it. But if it's not, then you don't do it. You know, is the need of having a list that grows and shrinks dynamically, man, is that worth me implementing? If it is, you do it. If it's not, you're like, no, an array is perfect, because arrays are fast, they have direct access, they're just cleaner, then yeah, you just use an array. But arrays don't grow and shrink nicely. I mean, even when you use vectors and standard template library and they do everything pretty efficiently and awesomely, it's not as clean as just not ever doing it. You know, you still pay, you got to pay somewhere for all those operations. So if you put 10,000 items into a vector and then you delete them one at a time, you're still paying a lot, because every so often that vector's got to resize itself, reallocate memory, copy everything over to the new smaller one or the new bigger one. You're paying somewhere at some way. So I tend not to use standard template library a lot because I want us to implement everything. maybe, I don't know. Because one of the first assignments I do like to assign is make you guys create an array-based anything and have to grow and shrink the array on your own. And I think I'll just stick with that as a first assignment. I'll be posting it pretty soon. But all it is you managing the size of the array. And then I have data that I make you insert. Actually, it's a stack. And yeah, I won't go over it now. We got 5 minutes left. I think we're all spent. Are there any questions? So yeah, I didn't even give you guys really time to ask anything, did I? Oh, let me keep sharing my screen, but I want to show you something. Okay. So yeah, this truly is a topics list. I'm going to try to stick to this. We'll talk about complexity next week and we'll check these off. I'm going to make a calendar because I promised Byron I'd be more organized, but we're going to have, because my OOP class last semester, it sucked. We were all over the place. It was bad, but I think everybody had a bad semester. So I'm gonna put where we're gonna have a test, and then I'll schedule it, and so we'll all know what's going on. Some of these have links to content. There's also, I don't ever make you guys buy a book. All this is free stuff, but I'm also creating course notes. Last semester for OOP, I did it, and everybody kind of liked it, I think. And hold on. So I'll do the same thing here. So in Maine, I'm getting up chapters for everything. So basically, this will be a compilation of all the stuff we do. How to comment your code. Any code I do, I'm going to create gists and link to them. Let this compile, it'll show you. All the data structures we talk about, I'll try to put in here, but it's just course notes and it's organized. Yeah, this is called LaTeX, by the way. It's what they write, what we write, like publications and stuff in. It's really big in math because you can really format things nicely. So yeah, I'll have course notes starting to get posted pretty soon. I had to clean up the introductory chapter, and then I'll post it, and then it'll be a living document. It'll just keep growing as we go on into the semester. And stop sharing. Whew, now I'm tired. Now I can go drink some bourbon. I need to work out is what I need to do. Any questions at all? Was that too fast and furious?
Okay, but bourbon's right there.
Huh?
Working out's okay, but bourbon's right there.
Yeah, maybe that is work out and drink bourbon.
There you go.
No, seriously, was that like fast and furious? The pace, was it too crazy, or because like last class we faded off at the end. I stopped explaining things as well. Did I keep up with the explanations this time? Were you guys following?
Yeah, you did better on this one.
One more time. Who said that? No.
Yeah, you did better on this one than the OOP one.
Okay. Okay, good. But that pace is okay then. And as long as I comment, I'm feeling like you guys, I always assume you can still see my screen, but as long as I comment the code, put it on GitHub, and we're recording it. So I'll make that available somehow. Yeah, you guys should be good. There's plenty of stuff. Okay. Nothing else? Then we're good. All right. See you guys.
Have a good weekend.
You too.
Hope you have a nice weekend, Dr. Griffin.
Thank you. See you guys on Tuesday.